Welcome to Biogas Basics. My name is Jürgen Kube. In part 4 of the mini-series about the substrate system of A-D plants, I talk about the pumping system. I will discuss how to connect digesters and tanks with pumps and pipes, and how not to. Let's start with an example biogas plant. It comprises two parallel primary digesters, a secondary digester, a digestate separation step, and a storage tank. Some of the process water must be pumped upstream to the primary and secondary digesters for dilution. So, how should the pumping system for this plant look like? First, we calculate the mass balance as shown in presentation 4.1 to determine all mass flows between the different process units. The plant feeds 100 tons per day solid and 20 tons per day liquid feedstock. The feedstock properties are shown in the table below. The solid feedstock is fed through a liquid feeding system where feedstock is commingled with digestate from the primary digesters, and the mix is pumped into the primary digesters. Liquid feedstock is pumped into the two primary digesters. The primary digester can operate at a maximal total solids of 11%. The effluent from the primary digesters is pumped into the secondary digester. From there, the digestate is pumped to the separator. Solid digestate drops into a bunker, the process water runs into a process water tank from where it is pumped into the primary and secondary digesters for dilution. Excess process water becomes liquid fertilizer and is pumped into the storage tank and eventually leaves the site. We can do the mass balance and now know all mass flows. The total amount of liquid streams that need to be pumped are almost 1,400 tons per day, plus another 1,600 tons per day of feedstock and digestate mix from the liquid feeding system. The pumping system of biogas plants can follow two different philosophies. The first philosophy is the centralized pumping system. Often, this comes in the form of a pumping container manufactured in a workshop and shipped to site for installation. This pumping system is prevalent on small agricultural biogas plants. The general idea is to have two large header pipes and connect every tank to the suction and discharge header. A pump connects the two headers. A standby pump can be installed parallel to the duty pump to guarantee high uptimes of the biogas plant. We can pump from primary digester 1 and 2, from the secondary digester and the storage tank to the primary digesters 1 and 2, the secondary digester and the storage tank. The import tank for liquid feedstocks is connected to the suction header and liquid feedstock can be pumped into every tank. Further, the dilution stream for the liquid feeding system at primary digester 1 and 2 is connected to the discharge header. We can use digestate from the primaries, the secondary, and even from the storage tank and import tank to dilute the solid feedstock before feeding. Especially when the viscosity in the primary digesters is high, this seems to be a good idea. I will explain later why it's not. Lastly, we connect the separator to the discharge header. Process water flows from the separator into the process water tank by gravity and is pumped out via the suction header. We can now separate from every digester and pump process water into every tank. The table shows all flows that go through the central pumping header. In total, 1,383 tons per day will flow through the header system and pump. The pump should not run longer than 16 hours per day. The pump will see some downtime, and it will take in a couple of seconds for valves to open and close every time a pumping routine is stopped and another starts. We can calculate the minimal pump size by dividing the total flow by the maximal runtime. Here, the pump must be able to flow at least 86.4 tons per hour. We choose a nominal pump flow of 90 tons per hour. Not only must the pump be able to pump 90 tons per hour, but all process units that use this flow must be able to handle the 90 tons per hour as well. These include the separators and the liquid feeding system at the feed hoppers. The liquid feeding system adds the solid feedstock to the dilution stream. The flow back to the primary digester is slightly higher, here 103 tons per hour. Each feed hopper must discharge the daily dose of feedstock 50 tons within 3.9 hours. The mass flow out of the feed hopper is 12.9 tons per hour. This will require large augers or conveyor belts. The separator must process 248.8 tons per day within 2.8 hours. The flow to the separator is 90 tons per hour. The process water tank must have a reasonable size because the separation must stop when it is full and the pump must empty the tank before separation can recommence. The central pumping system has only one duty pump, with 16 automated valves that adjust their positions depending on the flow's origin and destination. For simplicity, I only show valves that contribute to flow selection, excluding those with a safety function. Now let's compare this system with a decentralized pumping system. Each primary digester pumps into the secondary digester with a dedicated pump. The secondary digester pumps digestate to the separation unit. Process water from the process water tank is pumped to the primaries and secondary digester and storage tank. And with some clever pump control, the process water tank can be omitted. We can connect the import tank to the same header system to pump liquid feedstock to all 4 tanks. The liquid feeding system has dedicated dilution pumps. They pump digestate from the primary digester to the respective feed hopper. The feedstock digestate mix is pumped to the primary digester. The decentralized system has 7 pumps, excluding the liquid feeding system, but only 5 valves in the process water and liquid feedstock header. Because the pumps can run independently of each other, they can be sized for smaller volume flows. The table shows the pump flows and times. We choose a 15 ton per hour pump for the primary digester. It operates around 6.8 hours per day. The separator feeding pump at the secondary digester has a flow of 30 tons per hour. Consequently, the separator and the process water pump must have the same throughput, though the process water pump runs at a slightly reduced speed because some of the mass flow to the separator ends up in the solid digestate. The separation and the process water header operate for around 8.3 hours per day. Liquid feedstock is pumped slowly with a small pump at 15 tons per hour to the primary digesters. This will use the process water header for another 1.4 hours. The dilution stream to the feed hoppers is chosen to 30 tons per hour. The feed hoppers are active for 11.7 hours per day and must discharge 4.3 tons solid feedstock per hour. In total, the 7 pumps operate 54.8 hours per day. Of course, it is possible to combine the 2 systems, like in the example shown here where the feeding system has dedicated dilution pumps. As a result, the central pump can become smaller, here 50 tons per hour, but the plant retains most attributes of the central pumping system. Another possible modification is to split the headers into 2 sections that can operate independently. This allows to pump from the primary digester to the secondary on the left side of the header, shown here in yellow. While on the right side of the header, the secondary digester can be pumped to the separator, shown in green. It is also possible to extend a decentralized pumping system with a centralized pumping header. I recently came across this system and thought it was an elegant configuration. It retains the advantages of a decentralized pumping system and gives the ability to pump from every tank to every tank. Simply connect the discharge side of all pumps to one central header pipe. This is not an expensive modification. The valves can even be manually operated valves. In normal operation, this pipe is not used, but it gives additional flexibility. For example, if a primary digester must be re-inoculated from the secondary or the other primary digester after a degrid. Just don't forget to flush the pipe with process water after use and keep one valve open to the process water system. Let's compare the 2 systems. Many advantages of one system are the disadvantage of the other. The centralized pumping system allows full flexibility. The operator can pump from every tank to every tank. They can dilute the feeding stream with digestate from the primary or secondary digester, or even with separated digestate or liquid feedstock. Digestate from primary digester 1 can be used to dilute feeding to digester 2 and vice versa. It is also possible to feed both digesters from one feed hopper. The decentralized pumping system allows only downstream pumping, primary to secondary, and secondary digester to separation. Process water and liquid feedstock can be pumped into all tanks. The feeding systems 1 and 2 can only feed the respective primary digesters. This pump scheme is less flexible than the centralized system, but the reduced flexibility can be a good thing. It disincentivizes the operator from incorrect operation of the plant. For example, it is not possible to pump from the secondary to the primary digester stage, which would lower the conversion efficiency of the plant, or pumping unseparated digestate into the storage tank, which will lead to floating layers. Sometimes, a flexible pumping system is an excuse of the plant designer to let the operator figure out how to run the plant. The centralized pumping system can apply a standby pump in parallel to the duty pump. This allows maintenance works without plant downtime. Standby pumps in a decentralized system with 7 pumps are not common. However, all the pumps are either 15 or 30 tons per hour. It is possible to hold spare pumps on site and swap them out within a day if they fail. And they will fail less often than in a centralized pumping system because of the lower flow rates, pump pressure, and pumping times. The centralized pump system is common in small-scale agricultural biogas plants, but this system will struggle when more tanks are added to the plant. At some point, if the plant is expanded or the diet changes and more dilution is required, the central pump will be in constant operation and will become the limiting factor on the plant. A biogas plant with a decentralized pumping system can easily be expanded by another primary digester. The volume flows in the centralized pumping system are high compared to the decentralized system, and so are the velocities and the pressure drops in the pipe. The suction lines in a centralized pumping system can be very long and will most likely contain several high points that can accumulate gas. The suction lines in a decentralized pumping system are short and can be built without high points. Why is this a problem in a centralized pumping system? It has an effect on the viscosity that can be tolerated in the primary digesters. High velocities and viscosities mean high pressure drops in the suction and discharge pipeline. A high pressure drop in the discharge pipe can simply be overcome by a higher pump pressure. A centralized pump system requires more pumping energy than a decentralized pumping system. A high pressure drop at the suction side can stop the pump from working. In conventional applications, a pump can cavitate if the pressure drop on the suction side of the pump becomes too high. The required net pressure suction head, or NPSH, must be smaller than the available net pressure suction head to prevent a pump from cavitating. NPSHA must be larger than NPSHR. The phenomenon changes when digestate is pumped. Digestate is oversaturated with dissolved CO2. When applying a mild vacuum, CO2 will degas from the liquid. This is not cavitation. The CO2 bubbles will not implode after they have been produced, but simply stay entrained in the digestate. This effect leads to a higher pressure drop and can even create pockets of gas bubbles in the suction line, commonly known as vapor lock. Furthermore, the gas bubbles add an elastic property to the digestate. Instead of pumping digestate, the pump will simply deform it if the gas holdup becomes too high. Considering all those effects, the suction lines on digested pumps should be as short as possible. A direct consequence of this is that centralized pumping systems only work for low viscosity applications. If the digestate has a high viscosity, a decentralized pumping system is the only feasible option. High viscosities mean high pressure drops and high gas holdups, and that will worsen the effect of a vapor lock in long suction lines of central pumping systems. Process units that are fed from the centralized pumping system must be designed for a high throughput. In our example, the separators must be able to process 90 tons per hour while operating for 2.8 hours per day in the centralized system, and process 30 tons per hour for 8.3 hours per day in the decentralized system. The feeding system shows similar behavior. It must be able to process 12.9 tons of solid feedstock in 3.9 hours per day to create a feedstock digestate mix of 103 tons per hour in the centralized system. In the decentralized system, the feed hoppers operate at the third of the throughput, but for 3 times longer. The process units can be designed smaller in a plant with a decentralized pumping system. The smaller units have a positive impact both on capital expenditure and operating expenditure. The next point does not appear to be a problem at first glance, but it has significant consequences for capital expenditure and plant availability. The process control of a centralized pumping system is far more complicated than that of a decentralized system. In a decentralized system, the pump routine must check the levels in the source and destination tank and can start pumping if all conditions are met. Pumps can run independently of each other whenever the process demands it. In a centralized system, pumping tasks must be prioritized, which makes the PLC more complicated. A complicated PLC leads to longer commissioning times, more troubleshooting, and a lower plant availability. Further, the pumping system affects the ability to extend the plant. A biogas plant with a decentralized pumping system can easily be expanded. Simply add another tank, pump, and pipeline. But a plant with a central pumping system will probably struggle with an additional tank, as this tank must be pumped into and out of using a pump which is already in high demand. Especially if the central pump is used in the feeding system, the central pumping header is quickly overwhelmed. More digestate must be pumped to the feeding system to dilute additional feedstock. The additional feedstock is converted to additional digestate, which must be pumped from the primary to the secondary and from the secondary digester to the separation. Because of a higher substrate load, the primary digester thickens up, and additional process water must be pumped into the primary to dilute it. And consequently, the additional process water volume must also be pumped from the primary to the secondary and from the secondary digester to the separation. Simply exchanging the central pump for a bigger version does not really work. The higher volume flow leads to a higher pressure drop, which exacerbate the problems on the suction side of the pump. So, a centralized pumping system severely restricts the AD plant's potential for expansion. Both the centralized and decentralized pumping system can be modified to lose some disadvantages, but will retain most of their characteristics. To conclude, I would always prefer a decentralized pumping system. This episode about the pumping system on biogas plants ends here. In part 5 of the mini-series about the substrate system of AD plants, I will discuss feeding systems. Thank you for watching, and I see you in the next episode of Biogas Basics.